We investigated the local formation, the structure, topography, morphology, and properties and chemical composition of the solid electrolyte interface on hard carbon anodes, which are the main choice as anodes for sodium-ion batteries. For the sample preparation, we embedded the electrode and polished it and investigated the cross-section to have a super smooth surface and to have single particles separated but still electrically connected with each other through the binder carbon black matrix. And the novelty here now lies in the ability to investigate the SEI formation locally on a single hard carbon particle under varying cycling conditions. In a usual battery we have thousands to millions of active particles. However, here our aim was to probe the properties on a single particle level of hard carbon anodes in the glove box in argon atmosphere. Our focus was on understanding how the electrolyte composition, the cycling conditions, the scan rate and cycling number influence the thickness of the SEI. And we were also interested if our scanning probe microscopy approach can contribute to conform the model which describes the SEI and offers a completely different perspective on the structure and function of the SEI. So we used here a combination of advanced microscopic and spectroscopic methods in a collaborative effort. We have a scanning probe microscope in the glove box with which we can perform atomic force microscopy measurements, AFM measurements, and especially we can mention the conductive AFM, CAFM, to characterize the SEI morphology, thickness and insulating properties of sample. And we can also perform AFM phase mappings and force spectroscopy to study the nanomechanical properties and the chemical nature of something is organic or inorganic of the SEI layer. And with the very same piece of equipment, we can change the scanning head to switch from cantilever-based system to a capillary-based system. And this now allows us to perform measurements with a technique called scanning electrochemical cell microscopy, SECCM, where we can now locally study or locally form the SEI layer, microspots under controlled electrochemical conditions. And here we have definitely to mention the fantastic work of other groups, for example Professor Unwin from Warwick University in the UK, who basically introduced SECCM as a technique and who showed that it can be used with lithium-ion batteries on model substrates like HOPG. And as another technique that we have also used in a collaborative effort, we have to mention the time of flight secondary ion mass spectrometry, actually also combined with AFM, so a AFM ToF-SIMS device that allowed us to gain 3D mass spectrometric imaging data and chemical composition analysis. And besides that, we did some studies to back up all the data that we observed by Raman spectroscopy, contact angle measurements, and energy dispersive X-ray spectroscopy. So we could show that we can, with our scanning probe microscopy approach, show for the first time that we can get SECCM spot-derived SEI layers that we can then further investigate, and under the given experimental conditions, we could see that the SEI layers that we formed consist basically of two layers. We have a thin, uniform, inorganic rich layer and a thicker, heterogeneous outer layer. But we have to mention that the SEI's structure and properties strongly depend on the used electrolyte, and here we investigated two electrolytes. We had a carbonate-based electrolyte, ECPC, where we found that the SEI is in general thicker, ranging from a few nanometers to several hundreds of nanometers, and continues to grow with more cycling. And in the other case, we had an ether-based system, decline system, where the SEI formed always as a thin, stable and very uniform layer, and basically when we continued going to more cycles, we didn't see a growth in thickness. We also saw that with higher scan rates we get more heterogeneous and more incomplete SEI formation, and the ToF-SIMS measurements confirmed the presence of some compounds such as sodium fluoride or different sodium oxides and organic fragments, reinforcing the layered model to describe the SEI. Well, here we have to again keep in mind that the electrolyte system heavily influences the SEI layers. So our observed structure supports the layer-by-layer model rather than a mosaic model of the SEI formation, and we always saw an inner layer. This is a very thin layer in a range of a couple of nanometers after one cycle. It is very smooth, it is very uniform, it is mechanically stiff and less adhesive and insulating and directly forms on the hard carbon surface. And then we have also found an outer layer which is thicker, which for decline was 40 nanometers after one cycle, and for the carbonate-based solvent system, it could range up to several hundred nanometers after 40 cycles. It is mechanically softer and more adhesive, and likely results from electrolyte decomposition, and was confirmed by phase imaging and AFM force spectroscopy that is more adhesive. So we used scanning electrochemical cell microscopy as a very localized technique. As hard carbon composite electrodes, they consist of, besides the active material, of binder and nanocarbon mixtures with hard carbon black particles. Therefore, the SEI may unevenly form across the electrode surface, and here we now can fully exclude the contribution of, for example, binder and additive areas, because we only probe the active material particle surface here. And also it allows us to measure the thickness, which is absolutely challenging if we would consider a fully cycled electrode, because here now we have a single active particle which is only partly covered with the SEI, so this makes it very easy for us to determine the thickness. And another aspect that should be considered is that we have now only the interaction of the electrolyte with the active material particle, and we were able to compare the chemical composition that we determined by ToF-SIMS measurements, and we figured out that if we compare the microspot probed fragments compared with a fully cycled electrode, we saw that some signals are missing. So basically this brought us to the conclusion that there must be some processes where side reactions are involved, not only with the hard carbon active particle. So for future plans, we want to use the SECCM, the scanning electrochemical cell microscopy, to study SEI formation across various anode and cathode materials and also different electrolyte systems, since we are here absolutely not limited on a certain battery chemistry. And with this localized approach, we are able to perform rapid screening experiments, because we have one sample with a lot of different active material particles. So after we finished one experiment, we can simply move the capillary to a different position and then could rapidly identify relevant cycling parameters and establish cycling protocols. And in the case of the hard carbon work, we are currently conducting conductive AFM studies, so-called IV spectroscopy data, so current voltage spectroscopy, where we could basically get deep insight into the insulating properties of the differently formed SEI layers.